Hello guys, DataPandas here. If you don't know me yet, I'm a software engineer and data scientist, and DataPandas is an ongoing project that will help you to create your little own coding knowledge. So today we are gonna see a crash course about data structure. This is an overview. It's a very simple overview and don't pretend to be very accurate course. Is just a crash course that is very handy even if you are a beginner in data structure or if you are a pro and you want just to refresh your previous knowledge and use very handy schema that we are gonna see during this course. But let's jump directly into the course. So, what is data structure? Data structure is a collection of data values, the relationship among them, and the function or operation that can be applied to the data. So data structure is not only a collection of the data, but it's very important to understand that is the let me take a note. That is the relationship as well. The relationship is very important. The relationship among the data. So not only the collection itself, but even the relationship. How the different nodes are connected, how the different nodes are the relationship. So basically, the concept important is the relationship. We can see, for example, it's not itself. Data structure, it's not, for example, the number 1, the number 2, or the number 3, but very important part that is exactly also the arrow that we are gonna see here, or basically the relationship. Well, basically, being a software engineer means using a data structure every day. If you are a backend developer and you want to access the database, to pass some data to front-end, to backend, every time that you need to work with data structure is inside our life. Even if you are not a software engineer and I don't know, if you have to do, for example, your grocery, you have to do a list. Sometimes someone orders this list in relationship with the position of the product inside the supermarket. But every time, even for a front-end developer as well, sometimes has to get the data and using some manipulation algorithm to render the data or add other manipulation step before rendering the values. Of course, machine learning engineer as well has to work with the data to clean a dataset. For example, cleaning the null values, for example, fixing wrong data format in a dataset, and so on and so forth. Every time in our life, even if you are not a software engineer, you need to work with data. And the data structure, especially in software engineer, is very handy to understand how data is connected. So, but let's jump now into the difference between the data, between the different data structure. So, data structure is divided mostly. This is this is a crash course. So we are gonna see the most popular. The very popular data structure is not for everything. It's not for everything, but this is the most popular data structure. So let's say, for example, that we are gonna see. Let me delete this part. That's it. So this is the most popular. Don't forget that it is the most popular. So basically there is a strong differentiation between the data structure that we are gonna see in this slide, and the greatest difference is about the linear data structure and the non-linear data structure. So basically the difference is that the linear data structure stored the data like a line, basically like a line. You can imagine not a hierarchical structure like non-linear. Non-linear is typically hierarchical organization of the data. So inside the non-linear we have the tree that we are going to see in detail in this course, and we have the graph. It's very similar, the graph, to basically a tree is a graph, but with special condition. And the linear structure, we're gonna see basically another difference between the static and the dynamic structure. In the static we have array, and the dynamic we are gonna see linked list, queue, and stack. And this is what our course want to explore. So here you can see a slide about big O notation. Why we are gonna see a slide about big O notation? When we study about data structure, a very important steps that we need to understand is what we call the complexity of an algorithm. And it's extremely important because understanding the time complexity concept, let me take a pen, understanding the time complexity time complexity and space complexity concepts is very important. It's very important to understand how good is an algorithm. So basically, I'm gonna show you my website where that can help you to understand better and follow my steps. So here you can see my website. Basically, you can access to my data structure course. And in this page, like we said, we are going to see the most popular data structure, the definition of data structure. I'm going to show you basically how to use my website, how to get the most value from using my web. Don't forget the website is webdatapandas.com. You can access to the home page, and in the home page you can see all of my lessons. Basically, this one is the 3 TikTok, and this one is 3 YouTube video. I'm gonna create, I think in my process I will create more YouTube video because I can explain better complex concept. So if you go inside my article, you can see here, I'm gonna show you the definition. I already showed through the PowerPoint, the complexity analysis, and this is the concept, the very important concept behind the data structure, the concept of complexity analysis. And basically is about, this is involving two sub-concepts. The one is time complexity and the other one is space complexity. So in the context of coding application, we build an algorithm that we want it fast as much as possible and that takes up less memory as possible. And to measure those both quantity, we needed to introduce the concept big O notation. And big O notation is a very popular concept to analyze basically, of course, for mathematical analysis and study of function, but in particular for asymptotics that is called asymptotic analysis. It's not always in, it's not only, in computer science, but is in a lot of different mathematical fields. But before starting the complexity analysis, we need to understand another concept, very important concept, that is the memory. So I'm gonna return in the slide and I'm gonna show you the memory. So let's say for a moment, let's concentrate for a moment in the array representation in the memory. So what is the memory? You can imagine basically memory like a canvas. And basically in the memory, you can store the data with the basic unit of information, and the basic unit of information is called bit. So we have the bit, that is the basic concept, the basic unit of information in computing and digital communication, and any data stored in computer in such a way is represented in bits at lower level. What is bits? Bits basically is probably you already heard about a binary number. If you don't heard about it, you can just Google it. It's a very concept, very simple. In 5 minutes you can solve all your doubts on binary number, but basically is a way to represent a number. So bit basically can assume two values, or 0 or 1, and with this value we can represent all the number. We have another concept very important to introduce, that is the byte. The byte basically is 8 bits. So it's a group of 8 bits. So say for example, since a binary number is a number expressed with only 2 symbols, like 0 and 1, a byte can effectively represent all the numbers between 0 and 255, because 255, it means 2 high 8, basically. Of course, 2 high 8 is 256, but we start from 0, so the max number that we can represent is 255. So this is the basic concept about the memory, about how we work the memory. But let's imagine a memory like a canvas, and I can move this concept out from here. So just for a moment we can, let me copy. Just for a moment we can forget about this value. We can investigate on it later. About how an array works, but basically when I stored a data, I say to my memory, for example, I want to save the number 1. So to save the number 1, I can use a representation of the number. In particular, it's very famous, the 32 bytes representation or 64 bits representation. And basically, if we want to represent a number, say for example 1 in 32 bits, what we can do is just using this cell to save the value. So let's say for example that each cell save a byte, so 8 bits. To represent the number 1, we can do just 1, 2, 3, 4, 5, 6, 7, 8, and then the first byte is saved inside the first cell. Then we have the second byte saved in the cell number 1, then another one in the cell number 2, and in the fourth we have the representation of the number. For example, this is the number 0, and this one is the number 1. So in a system with 32 bits, sorry, let me remove the fill here. So basically here, this one is a representation in a memory of a number. So I'm using this cell to save the data in binary format. So regardless of how large an integer is, its fixed with integer representation is by the definition made up of constant number of bits. It follows that regardless of how large an integer is, an operation performed in its fixed with integer representation consists of a constant number of byte manipulation, since the integer is made up of fixed number of bits. So we need all our investigation, all our manipulation involve these bits and the version with the bytes. So in the concept of computer science, it's important to note the following point. So data storage in memory, like we see, is stored in bytes and by extension in bits. Bytes in memory can point to other bytes in memory, so as to store referenced data to another. So let's say, for example, here, if I want to connect, this is the number one. So like we say, let me jump, let me, for example, insert another text box. Okay, this one is the number one. Let me increase. Oh, just a second. Okay, I can copy this one. So like we say, this one is the number one. Let me increase the size of this number, and this is the representation of number one. Another way, I can use a memory also to connect the data. So let's say, for example, let me open this slide. So another things that we can do is just, so this one, like we say, is the representation, let me take a pen, is the representation of number one, and I want to connect the number one to another slot of memory. What I can do is using the number 4, the cell number 4, to connect and give a reference. So here I can put basically a reference. A reference is as well a bits reference to another object. Say, for example, is here in the memory, and here I have another object. Say, for example, the number 0. So even this one is a cell of memory. Okay, this one is the number 0. So I reference in the memory, I can do this one as well. I can create a point to my number 1, that is this one, to the number 0 that is here. I can do also this one if I want. Of course, the amount of, another important point that we need to understand, that we need to memorize, that the amount of memory that a machine uses is bounded, making it variable to limit how much memory an algorithm takes up. Is very variable, reduce the number of bytes, of bits that we are going to use during our coding application. It's very important, reduce at the minimum, as much we can do, of course, the amount of memory that we take it. Because we have not forgot that this memory take each shell. So here, let's imagine that our PC, our phone has only, this is 20, it has only 20 cells. And with 20 cells, we need to stay careful because the memory can finish it very, very, very quickly. Of course, our PC has million and million and million of cells, but even with so big data in the world, we have to stay careful because the memory is bounded. We don't forget that the memory is bounded. And we can assume also that accessing a byte or a fixed number of bytes, amount of memory, that a machine has for a machine is an elementary operation. So accessing, for example, to this one is a very elementary operation, and is a very fast operation in the memory. So basically this one is the concept that we investigated about the memory. But we can jump again in the previous slide for a moment, sorry, about the big O notation. What big O notation does it mean? Because once we understand the memory, we need to understand, so let's say, imagine a memory like a canvas. And this basically stored, the data was stored in bytes, the data is stored in bits at a lower level, but anyway, this one, it's fine, we don't need to investigate more on the memory. This is just a crash course, don't forget, this is a crash course, so only the basic, I want to give you just the basic. Let's concentrate about big O notation. So the big O notation is very important because we use big O notation basically to study two sub-concepts that are extremely important. So the time and the space complexity. And basically here you can find the most common function that is used to represent the big O. So like you can see in my website, so if I go just a second down, you can see that the notation used to describe and measure time complexity and space complexity is an algorithm, is big O basically. So the following example are the most complexity and the big O notation ordered from the fast to the lowest. And now we need to understand what does it mean, this table. Because we have O1, log n, ODn, O of n, sorry, On multiply log n, and On square. What does it mean? What does it mean here when we are talking about big O notation? So basically, what we need to understand about the big O notation, we need to jump into example to make it more clear. So let's say, for example, I have a function, number one, that basically take an input an array, and in this array, what we can do in this function is basically get the zero element. Or to explain better, the item that is in the zero index position in an array. And the function number two that basically sum all the items inside the array. So we need to understand the complexity. Which one is more complex? The function that take an input an array and return the items at zero index, or the second function that sum all the items? The response is very simple. Of course, is the function that return the sum of all items. But how much is the function one has, of course, function one has a time complexity, function two has a time complexity as well. And of course, the times complexity of f1 is less than the time complexity of function two. But how much less? How can measure this time complexity and understand how much an algorithm is better than another one? So basically, time complexity means at the lower level means time. So time means basically how much seconds this function is taking. Basically, this one is the concept. And from the time I mean actually the seconds, the minutes, the hour that this algorithm spends. Because basically at the end of the day, the most important part is how much time our algorithm is taken. This one is the most important part. And we can just measure using, for example, the code, directly the code. So I already created a code that basically what is doing is the first code is taking an input array, and the second code what is doing is basically sum all these items and return the value. So let's say I want an array that I want to create an array that basically is taking time. So let me just a second restarting this kernel, probably is too old. And I can import data time, and I have, so basically I have two functions. Let's, for a moment, we cannot study about this function. I want to show you just the first function. So import the time, because that's why I'm importing the time, because I want to measure the time, the seconds. And now I'm going to explain in deeper how to create an abstract concept of time complexity that is not about the time, but is about more measurable things. Because the time, the time of a function can depend on, for example, the PC, can depend on how much RAM free I have. It's depend on how my PC is performing. So the time in itself, it's not good to understand an algorithm, what is under the hood of an algorithm, but it's very handy to understand practically what we need to do, how complex is our algorithm. So let's say I created an array from 1 to 100, and I want to give two functions, the print one and the sum of all these value. And here what I'm doing is simply let me zoom a little bit. So I want to print this value, and so first of all I create a now function before starting my function, and now after starting my function, and I create the difference between these two functions. Let's see, very simple. So like we can see here, so the first one is very fast and the second one is very fast as well. Basically there is no difference. If I run it again, like you can see, there is no difference. It's 0 seconds and nothing. It's extremely fast. But what's happened if I increase the memory? So there is no difference. At this time you can see there is no difference between these two values. But what if I, for example, I had 1000? Let's run it again and let's see what's happening. Again, 0 time. So we cannot, for example, if we work in a context where we don't have big data, we don't have it's not big data, but is the correct words is the large amount of data, because big data is another concept. We will make a video on that. And so basically, like we see, there is no difference. If I run this one 100 times, you can see there is not significant difference. Okay, let's say the sum, and that's it. And here is returning is printing the first value of the array. Let's say, for example, I add another 0. What's happening if I add another 0? So if I go here and run it again, let's see if we have some difference. So let's run again. So basically no difference. The time is very, very similar here as well. So let me add 2 0 and we see if we are gonna see some difference. So let me run now. So see, this algorithm looks a little bit slow. So every time that I'm trying to print this value, like you see, this one is fast as well, like in the past. And this one, it starts to be a little bit more high level. A little bit more. This is one, but even now it's extremely fast because it's millisecond, it's nothing. But what's happening if I add, for example, other 30 here? And I run again the time. Let's see the time here. So, first of all, I need to create this array. And create this array with all these items require time. But just a second, we can just wait for the result. Because when the number become a little bit huge, required time to make the calculation. Probably too much time, because this is how much item are. Let's see, 30, yeah, is 1 trillion. It's crazy. So let me just stop for a moment. Probably this one take too much time for my PC. So let me restart the kernel again. Yes, because this one take too much time. We can investigating as well with, for example, we can remove a 0 here. So let's say 3. Let me remove 1 0 and 1 0. Okay, that's it. So much better probably. So I run again my function. I run again the import datetime. Okay, that's it. And now I'm gonna run this one. Okay, now we can see that is extremely difference between this time complexity and this time complexity. This is a huge difference. Because even with the so like we see with the very low value, with very low value, we can see that there is no difference, practically there is no difference between the print first value and sum all values. But if I push 1 billion of data, 1 billion, an array of 1 billion of item, the C is extremely different. So the print first value, the sum all values, the time complexity of sum all values is 10 times, probably 20. No, this one is 18 times, probably more, but it's extremely high. It's extremely high than the print value, or the first value. So print first value is millisecond, and sum all value is 1 second. So it's extremely, it's very close to 2 seconds. It's extremely high. And if I add another 0, the concept don't change. So what does it mean? The first print first value is very fast, even if you have 1 trillion, the hugest number that you can think. The print first value is very fast, because basically what it's doing is taking the first element. But with the second, I need to loop here all my item. And this one takes so much time. If the array is 1 million, 1 billion of data, here is not important because I'm taking the 0 element. So I don't mind how big is the size of this array. And this one basically is the concept of big annotation. The big annotation is concentrated about how an algorithm depends on the number of the row. So we can say, if I jump again in my website, so we can say basically that if a number if a function does not depend on the number of the item, say for example my function print first value, this one, print first value, does not depend on the length of this array, because basically it's taking the 0 item. This is the big connotation of this function is O1. Instead, the sum of value is a linear time complexity that is O of n. And then we have the different scenario in relationship to all the function that we can write. So let's say, for example, we have, this is in order from the fastest to the lowest. So the O1 is constant times, is very fast. The O log n is very fast as well. You can see here is very, very low. It's grow in very, very, very low time. We have O(n), that is a linear function. With this, we have O(n) log n, that is a little bit faster than O(n) and log n. And we have O(n) square. We have O(n) cubic, and this one here we come in ages, required ages to be run, very, very slow. So here you can find all my function that I wrote in my Spider notes, and here you can find also other notes about the time, how to calculate the time, and you can investigate yourself. So basically this one is the big annotation, and we use this one to measure the complexity of an algorithm. So if my array has n value, n is the number of, is the size of the array. So this one is very important because the time complexity and the space complexity as well we can measure with big annotation. Another concept that we need to understand is how can I sum two different big notation. So let's jump again into the code, and so like we say, the first one has a time complexity of O of 1 because it's run in constant time, and the other one has a time complexity of O of n because the complexity depends on the item, on the number or the size of the array that taken input. But what's happened if this function I put only 1? So function 2 in 1. What does it mean? What is the time complexity of this new function? Very simple, is the sum of the time complexity. So is O of 1 plus O of n. And this is one is equal to, a little bit spoiler, is O(n). Why? Because in syntactic analysis you have to imagine like the big one always win with the small one. This is a very, very, very crash explanation because around asymptotic analysis there is so much deep knowledge and you have to stay careful on a lot of detail, but at the end of the day, in the most common application, this is the basic concept that we need to understand. I remind you, this is a crash course, so we don't go deep in asymptotic analysis, but basically what you need to understand is that this one, the second item, is so much huge than the first one that basically the whole time complexity is O(n). And to explain why, because say for example, if I run again my array and I run this function, so let's say again I want to run the code, I have 1 second for the second one and exact zero for the first one, for the first function. But if I put together this function, in the function 2 in 1, the time, like you can see, is very similar to the time to the second function. Is very similar to the time to the second function and not the time of the first function. So stay careful on that, because if, for example, in the context of computer science, someone asks you how O of 1 plus O of n is equal to O of n. And in a similar way, if you, for example, using O, if, for example, an item has 100 row, or for example here you have to print the first value and you have to print the second one. Say, for example, this is O plus 1 and O plus 1, that is equal not, of course, O plus 2, but sorry, O of 2, but is, so this is completely wrong. This is yet O of 1. We don't have O of 8, 9, 100, etc. We have only O of 1. O of 1, that is mean that this function is running in constant times. And in my website you can see a very handy schema. So let's, for example, O of 1 plus O of 1 does not make O of 2, but of course is O of 1 because it's a constant time as well. If you have, for example, O of 1 plus 10 even is still O of 1, O of 9000 is O of 1, because is big O of 1 is a constant time operation. And the same with the other function. Let's say, for example, you can see here a lot of example, but if I have to sum two functions, one is running in O of 1, the other one is running in O big O of n, and the third one is running in big O of n square, always the bigger wins, because the oldest function is running in O of n square. Of course, in particular scenario, you have to stay careful, because if you have only O n square, so for example, let's say you have a function that is like this, and another function that is like this. Which one is better? Which one is faster? Of course, the second one is faster, because has only O of n square, but stay careful that for the two time complexity, for the two functions, sorry, the time complexity is exactly the same, and the time complexity is O of n square. Don't forget this concept, because you know because basically the time complexity is studying the worst scenario, is an asymptotic analysis. That this asymptotic means when the n is very, very huge, like infinite value. So in asymptotic analysis, it's meaning the worst scenario, it's mean when n is very, very, very huge, the time complexity is the same. So stay careful on this concept, and here in my website, don't forget web.datapandas.com, you can find a very handy schema that you can use. We don't speak about the logarithmic time complexity. This one is extremely valuable function in the context of coding interview. Here I just put down an example about when an algorithm has a time complexity of log n, because it's very easy to imagine, for example, a constant time function. We can build here. It's just printing the first value of an array. This is one O1, a constant time complexity function. This one is very handy to imagine, the O of n, that is a time complexity when you loop inside the cycle. And it's very easy to imagine, for example, a O of n square that basically is the same, but when I have two loops inside, This one is O of n square, but it's a little bit tricky to imagine how is, and of course as well, if I want a cubic, very handy to imagine, very difficult to run, but basically it's this one. I can have this one as well, but this one is a cubic. But it's very tricky to imagine how is the log n function. Basically, I build an example that, for example, let's jump into an example, like I say in my website. Now, we can just imagine that you are making a casting to get the third best mathematician ever. And in your casting, you got 1,000 people. You ask these people to take a test and vote, and the vote of the test is from 1 to 10. To take the best 10 mathematician, or third, I have to fix the website. You starting all this page will be published when my video on YouTube will be published. So you start cutting the people with some criteria. So because your test is very hard, the first slicing criteria is whose score is over 25. And you can, in 1,000 people, you can cut in half, and you got 500 people. Again, slice again, because you want to get your 10 best mathematician, 30 best mathematician. Again, slice the result and select the people whose score is over than 15. You got 205 people. And again, and again, and again, you are cutting your array in half at each iteration. So each iteration, suppose you have 1 million of row, each iteration you cut the value, and when you arrive, for example, with 15 iteration, your array has only, in this case, for example, 30 mathematician. So every time that you are cutting your dataset, you are reducing significantly the number in examining out. So in the context of coding, there is different balance structure. The most common is the binary search tree that use this concept to optimize the search. So this one is not a mathematical lesson on how the logarithm works, but basically, by the definition, if you want to investigate what is an algorithm, so let me a little bit rise here. So let me clean all of that stuff. Unfortunately, I cannot clean this point. No, okay, that's it. So if I want to go by the definition, the logarithm in a of b is equal to x, and basically what does it mean? This one is the exponent that we need to give to this base to get the argument. So basically I can write this function like this. And this one is extremely low function. That grow in very low time. It grows very slow. Typically when you cut in half the base, the A is 2, and the B and the X depends on the value that you have. So I'm gonna show you Excel. So this one is the n, and this one is the log n. So let's say, for example, that I have 1, and 1 is increased for 20 items. Okay, I want to calculate the log of this function in Excel. I can do as well in a paper. I can do what I want in base 2. Okay, let's see. This one is the 0 because basically is mean that we can just drag on all of that. Basically, what is mean that like we see here. Let me erase again. No, I can write here. So let me erase erase here. Okay, very good. And then, so basically the log in base 2 of 1 is equal to 0, because if here I have basically I have 1 that must be equal to no, sorry, this one here I have 2 because it's the basis. Don't forget that this one is the basis, the A, and I have obtained 1, and basically 2 hide 0 is equal to 1. So that's why the log in base 2 of 1 is equal to 0, because 2 hide 0 is equal to 1. And say for example I want to calculate the log of 2 in base 2 of 2 that is equal to 1, because 2 hide 1 is equal to 2. So the base here, the base is 2, and the exponent that I have to give to 2 to get 2 is 1. So 2 high 1 is equal to 2. And so on and so forth. We can do just, for example, the last one. The log in base 2 of 4 is equal to, very easy here as well, because we have 2x and we want to obtain 4. So this x must be 2, because 2 high 2 is equal to 4. So, but let's return again into Excel. So, like we can see here, basically we have this one is how slow is cloning the logarithm. So I can print this result. Let's say, for example, I want to create a map, a charts, sorry, and this one is the logarithm, and I want to compare, say for example, line. Okay, that's it. So this one in orange, you can see the log n, that is very slow, and this one is the n, how grow the n. Let's say, for example, that I want to compare with an algorithm that run in n square. If I want to compare with an algorithm that run in n square, so here I can put just basically it's this one per this one again. That's it. This one is so extremely fast. Let me do until 15. See the value? The value is so high. It's extremely high. I think it's difficult for Excel to represent in a very easy way. No, I can do it. So, like you see in gray, there is n square that grows so extremely fast, and the log n instead is very low. So you can find a recap on my website, and but basically an algorithm, for example the binary search tree, is using this type of structure to optimize the search. And here you can find a recap of all the roast function, the bad, the fair, the good, and of course the constant times, that is the best, because run in nothing, even if you have 1 billion of data. Okay, the next steps, here we go now in the data structure concept, the real data structure. So all the previous topics, all the previous conversation is about how memory works, how big O notation works, how the complexity analysis for the time and the space complexity is working, and now we are gonna see how is working the we can see the real data structure is in computer science. So we are gonna see basically the array, the stack, the linked list, the queue, the tree, and the graph. I remind, this is an overview, but could be very handy to understand the basic concept of computer science. So let's jump into an array. I can open again my PowerPoint, and I'm gonna show you the array. This is an array. Let me open here. Okay, now you can see for the first time, I don't know, it's for the first time, probably if you are a pro data structure engineer, you see this one so much time. But if you are a beginner, this one is very, very handy, because here there is a picture. Oh, sorry, this was a LinkedList. Here there is a picture of Arraylist. That's the picture. You can see clearly that is an array. This is how the array is stored inside the memory and how it works. Probably if you work with Python or Java, you can, for example, you are able to access to an array using just the index, because like the definition said, that we can read on my website, or in Wikipedia, or in so much website, that an array is a data structure consisting of a collection of elements, items, values, or variables, call like you want, of same memory size, each identified by at least one array index or key. An array is stored such that the position of each item can computing from its index tuple by mathematical formula. Extremely, extremely, extremely handy and powerful structure. So now you can see in the face the array. So let's say, for example, I have an array that has this value. So the value is 89, 11, 14, 8, 47, 90. And how this data is stored inside the memory? So basically what an array is doing is taking the memory and save this value, of course not in decimal like we can see here in the decimal picture, but the data is stored in bits or bytes, like we said in the previous topics, discussing on the previous topic. But here, just for a moment, we can think in decimal, because we think in decimal, but understand that the machine does not think in decimal, but in binary. And so with the bytes or with the bits in the lower level. So here we have this array, 89, 11, 14, 80, 47, 90. How the array is stored? So basically, array is pushing in the cell the value following the sequence of the value. So it's very, very handy. It's extremely powerful. If I want to access, for example, at the index 5, probably you already see the syntax. The syntax is array, and then you put the items, for example, in this case, the index 5, and you get the 90 item, the value 19. And this one is extremely, extremely powerful, because with a mathematician operation, you can get the value 19. This operation is extremely fast. Like we say, this operation run in O of 1, run in constant times, because under the hood is a mathematician operation. So because the array is stored the position of the first item, that could be here, but could be, for example, here. I have 89, I have 11, 14, 8, 47, 19, who knows, could be everywhere in the memory. But the array memory basically memorizes the index of the first position, change the name, of course, from 0, 1, 2, 3, 4, and 5. And with a very simple mathematical operation, once you have the first elements that you know where is in the memory, the 0 position, that is in the canvas is 13, like you see behind, the operation is very simple because you know that the first item is the 13, you add plus 5, and in no time, 0 time, you got 18. And 18 is the real position where you have the value that you are trying to get. So extremely powerful. It's just a sum. It's just a sum in 0 time, sum of two numbers. The reference, the first item, and the index. This one is the index. 0 time. So that's how array is working. Very simple. You can see now the array in phase. This one is very handy schema because it's very handy to see the array in phase. So let me rise a little bit. Let me removing all those stuff. Because now I want to have a conversation, an investigation about the time complexity of the array, how it's working. So if I say, for example, if I say here you can find, here in my website you can find all the time complexity, but why try to investigate on it. So let me put the note on the other page. And yeah, basically, so for example, if I ask you accessing a value at the head, accessing a value at a given index, what is the time complexity in the array structure, data structure of accessing a value at a given index? The time complexity, like we say, is O of 1, because basically is a sum operation. It's very simple. The reference and the index. Update a value at a given index, very extremely powerful, because I can get the value at this position and I can replace very, very fast. So if I want to update a value at a given index, is O of 1 as well for update. But let's say, for example, if I want to insert a value at the beginning, what I have to do? So here, I don't have more 89 or 18, but I have a number before 89. So before 89, I want to put another number. That is, for example, this one 47, this one is 90. I want to put a number that is, for example, 2 before 89. What I have to do is a very time-consuming operation, because I have to push all these items in the next position, this one 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 in the next position, and now that I have the first space empty, I can put the number 2. So, like we say, inserting a value at the beginning is an extremely time-consuming operation that required O of n, because I have to move n item. The same, for example, to insert a value at the middle. And the same, but not always, to insert a value at the end of the array. Because let's say, for example, that this is a memory. So let's try to investigating about insert in the end. So we can say end insert, because we say that to insert an item at the first item, it's very time consuming. Is OON. So insert at the start, it's very time consuming, because is O of n. And even insert in the middle is OON. But insert at the end, we have a little bit of conversation on it. And I'm going to explain you why. Because, like we see here, in the end of this array, we can have space. And if we have space, it's very handy to add an item. Say, for example, after 19, I want to add the number 2. So not at the beginning, but at the end. So if I have space, it's very easy. O of 1 is constant time, basically, because I have space. But what's happening if, because, you know, the memory, like we say, is bounded, has a limit, is not infinite memory. In our PC, in all the memory structure is bounded. So how we can, so probably, for some reason, this memory could be full. So here, we can store in the 6th position, we can store another array. That is, for example, 1, 2, 3, I don't know, 89, who knows? We can store another array. So probably the first array has not enough space to put the number 2 in the 6th position, because the 6th position is already occupied. Could be already occupied. So what we need to do is just taking all these items, search where there is 1, 2, 3, 4, 5, 6, 7. When there is 7 consecutive cells empty, and we can say, okay, here there is 1, 2, 3, 4, 5, 6, 7. Okay, I move my array here, and I say 89, 11, 14, 8, 47, 90, and here I can put 2. Okay, I can erase my array from here, I can have more space, and because only because the 6th position was occupied, I have to move all my array in a new position. So insert an item at the end is O of n, but is O of n only in the, what we call the static array. In the static array, for example, in Java, the default is the static array. Sorry, just a second. In the static array, we have an insert that is O of n. But we have another concept that is called the dynamic array. So just for a second, let me clean here. The dynamic array. So the dynamic array, what is doing the dynamic is basically take in advance some space. So let's say, for example, I have an array of, I don't know, here, how many are, 1, 2, 3, 4, 5, 6 items. I have an array of 6 items. But typically, the concept of dynamic array is taking other 6 place free. So 1, 2, 3, 4, 5, 6. This one, all these 6 space are empty and I'm using for my dynamic array. This is dynamic array. And this is very powerful because now, when the first time that I created my array, I take 6 position free, and now it's the end at the insert at the end of my array is constant time because I have enough space. So let's say, for example, I want to add another element 2, it's O of 1. So the insert at the end take only O of 1 constant times. I want to add another item, say for example, I don't know, 15 constant times, 16 constant times, 17 constant times, 92 constant times, 100 constant time. But stay careful, because when we full the empty space, again, we need O of n item to create more space. So stay careful. The dynamic array is very, very powerful, because take a little bit of space more, usually is the double of the size of the array, is taking from, is free in the dynamic array, the double size of the original array. But until we achieve the bound. When we achieve the bound, we have to again expand again our array, take more space, and transform the array again in dynamic array. So this one is the concept behind static and dynamic array that is extremely important in context of computer science. So let's say about other operation, deleting a value at the beginning. If I want to delete, for example, this value, how much time it take? Of course, O of n, because if I delete the item at the first line of the array, again I have to push this value here, push this value here, push this value here, push this value here, and again push this value here. So deleting an item at the beginning means that I have to push all my item back. Of course, there is some very handy structure that can increase the deleting operation, but usually in the usual implementation of the array, deleting a value at the beginning is O or n. Deleting an item at the middle is O of n. Deleting an item at the end, stay careful, because is O of 1. Because basically what I have to do is just deleting at the end my array and have more space. Very handy, O of 1. Copying all the array is an operation that taking all of n, and searching a value is O of n. Because, for example, let's say if I want to search the number 18, the number 8, I have to traverse all my array, and to take this value, I have to traverse all the array and search each value if I have my 8th item. So searching a value in the array take O of n time complexity time. Like I say again, you can find all this information in my website. Use my website as much as you can, because here there is a recap of all of this file. Just a recap, what we are saying that Arraylist provide constant times of searching operation, but searching, stay careful, when you read in Wikipedia, in so much website, when you mean search, it does not mean searching a value inside, but accessing, it means accessing. So I use the word search because so much website use the word search, but stay careful because it does not mean searching inside the value, but basically accessing at a given index. Because for search, of course, I have to, for search, of course, I have to cycle all my dataset. Because if I want to search number 19, I have to do a for. So looking at the first item at the 0 position, at the 1 item, 2 item, 3 item, 4 item, and I have to do a for to do that a loop until I get 90. So stay careful because accessing is O of 1. And when in the website you find search, it's mean not searching, but it means accessing, and search for a value, it takes O of n. So it's better to use Arraylist, is searching is more frequent operation than add and remove operation. Searching, again, not searching for a value, but accessing a value at the index. Probably I will change the word after, I will take a note of this to remember you that even in my website. So now we are gonna see the linked list, and like you see now, you can see in the face the linked list. So basically, this is the picture, of course in memory. It's a representation of how is the linked list saved in memory. like we said in the start of this presentation, let me go back for a second. We was investigating exactly the linear, and we spoke about the array. But array is a static concept, except of course for the dynamic array that we study together in the previous with the previous word, like we see before. And here you can see the dynamic object. The dynamic object, inside this folder we have the linked list, the queue, and the stack. That is dynamic. Why? What this dynamic word means? Means dynamic in the memory. Because here, like we see, like we saw here, all the numbers are saved inside the memory canvas, like 89, 11, 14, in a sequence mode. So we have a sequence. So 89 is near 11, 11 is near 14, 14 must be near 8, 8 must be near 47, 90 must be after 90 after B has to be after 47. So it's a static way to imagine an array, except the dynamic that save for us some empty cells, and we can use to have a dynamic concept. But in the linked list, like the queue, like the stack, and like the dynamic data structure, is very handy because it's not dependent on the sequence. So basically, this one is a very good representation on how the linked list is saved in the canvas. So let's for example, so I do an error here, because this one 11 is not the first element. Like we said before, our arrays consisting on 89. Sorry, our linked list 11, 14, 47, and 90. This is our array. But how is stored as a linked list in the memory? So we have the first reference, that is the first number, the 89, and the 89 near as another cell that point to another cell. Like we say, the memory is very good. Like we said in the first part of this video, memory is very good because it has a reference. You could reference, of course, speaking not like this is English, speaking with bits or bytes, we can reference to another object that in this case is the position 0, and this is 11. 11 has a position on 18, and from 18 we go in position in index 18, and the index 18 is here. So it's just moving here, going here, but the 14 has another reference, the reference number 3. So the reference number 3 is the number, in this case, 8. Sorry, probably I'm missing an 8 here, yeah, because our array has an 8 just exactly here, like the previous one. Just a second, yeah, because it's 18, 11, 14, 8, 47, 90. So I miss an 8 here. So in the reference 3 we have an 8 that is here. And the 8 number is a reference 7 that is here. Sorry, probably I'm missing 47. Just for a moment I can remove it. Let me remove it, the 47. So yeah, basically, yeah, so I'm missing the 47, but don't worry, we can just focus it on this array. So like we say 89, this is our linked list, sorry, 89, and this is 11, and this is 14, and then we have 8, and then 90. So let me just erase this one, we don't need any more. Yeah, basically that's it. So what's happening here? In the last we have 19 and then we have a reference to nothing. So it means that the linked list is finished. So this is a way, this is the phase of linked list. We can see a proper slide here, but basically this is how linked list works. Like the name saying, it's about the number and the link that is the reference to the other number. And this is very powerful, because the linked list should be used where every modification to a collection are very frequent, like addition and deletion. Addition and deletion, because we used array for basically to get, if we want to access easily to a given index, and we are using a linked list just to, if addition and deletion operation are very frequent. Why addition and deletion operation? Because we see, so let's speaking about some big O notation and time complexity concept. So let's talk about for a moment about the time complexity of the linked list. So say for example, if we want to investigating about accessing a value at the head, if we want to access to a value at the head of the linked list, that's very easy, because basically it's O1, so constant time operation. Like we said in my website, this is a constant. You have all this stuff inside my website, but basically it's a constant time operation. A constant time operation that, like you remember, is the faster time complexity that we have. So that's it. And basically another concept is about accessing to a tail, accessing a value at the tail. Take O of n, because I have to cycle, I have to jump in all reference. So jumping here, jumping here, jumping here, and jumping here until I don't get a reference 0. That doesn't mean that the value is, that it means that the value that is the tail, the last item of the linked list. So accessing a value at the middle node is O of I time. We can call just I time, because it depends on the position. If I have an array list, a linked list with 1 million item, and I have to access to, I don't know, for example, in the middle, I have to access to 500,000. And so basically this one, it's true that it's O and I, but we can assume like O of n. So, for example, if I want to insert removing the head, take O of 1, because this one is very easy, because all I have to do is just change the reference. I have to change the reference to the first item to another item. So let's say, for example, let me just for a second, let me clean here. If, for example, I want to add an item, the item that I forgot, for example, the 47, and I can put a reference here and say, okay, this one point to the reference 0, and this one is my new item. I remove this one, and I can say, okay, this one is my first new item. Very quick. So that's O of 1. It's not like an array. In the array we have to move all, in the array we have to move all of this stuff to the next position. So I have to jump to put 18 here, 11 here, 14 here, 8 here, 47 here, and then with the blank space here I can put 47 again. But here it's very handy in the linked list, because basically I have just changed the reference. And what about inserting or removing the tail? So let me erase here for a moment. Okay, let me just remove. And what about insert or removing the tail? insert or removing the tail. So if I have to remove, for example, the 19, this one unfortunately take O of n because I need to access to this item. It's not like in the array. In the array is very easy because I can access to the I index in very quick way, but here I cannot do that. So it's all the n time to access to 90, and then very easy because I have to change just the reference if I want to change this value. If I want to sort inserting an item at the end, I have to access, let's say for example, I want to add 47 again, so I can put just 47 here and putting the reference 0 here. But before do that, I have to access to 90, and 90 is in n position. So let's say for example I have 1 million items. This is very, very time consuming because I have to jump to 89 to the reference 11, from 11 to the reference 14, and from 14 to the reference 8, from 8 I have to jump to the reference 7, and only when I arrived at the tail I can insert an item or removing an item. So basically is O of n just to accessing to the last item, plus O of 1 because changing the reference in the linked list, it's constant time operation, very easy, even if I have 1000 million of row. What about what we can say, for example, if I want copy the linked list? So to copy the linked list basically is O of n operation, because I have of course to throw all the, I have to cycle, I have to jump in every single node of my linked list, and once I get all the value, so I have to do a loop of the linked list, searching all of item and then copying my linked list. Another things could be searching for a value, like in the array list as well. It's O of n time because I have to loop inside all my linked list, and this one can take n time. So if I have 1 million item and I have to search, I don't know, for example, for the number 14 could be everywhere. In this case is very easy because it's in the third position, because it's here basically in the third position. So 89 jump to 11 jump to 14, and I found the 14. But if I have 1 million item, I have to loop all the item until I get 14. So searching for a value is very time consuming as well. So we have the two types of linked list. It's very handy to speak about this kind of linked list. We have the double linked list. So basically every time I have a reference, this is for example my first item, this is the reference to the next item, but I have also a reference to the previous item. So basically that means that in your implementation you can have the method next, and you can have the method, for example, pre or previous. This one could be very handy, and this one is typically of double linked list. So each item is connected to the previous one. And here I have a circle linked list, basically when the head is connecting directly to the tail. And this one is very, very handy because if I have to work to the tail, for example, if I want to add an item in the tail, so in a circle linked list, take the inserting or removing of an item at the tail, it's O of 1. Remember that I remind you that in the simple linked list, insert or removing the tail take O of n, because I have to access to the tail, so I have to loop all in my entire linked list, and once I'm here, I'm there in the tail of the linked list, I can add an item. But in the circle linked list, basically is of one, because I have a direct link. The first item has a direct link to the tail, so the accessing is extremely fast. And of course, adding a reference, if I want to add an element, an item, or removing the tail could be very, very easily, because of course in the linked list this is the very powerful, the fast addition and deletion operation. So now we're gonna talking about another very important concept, that is the hash table, also called the Hashmap. And this is very extremely powerful concept that we can use in computer science. So how it's work? It's a little bit complicated to understand under the hood how the hash table works, but in this crash course we have to just see the basic concept of what is under an hash table, what is behind an hash tables, and basically just think on this, just take a look on this. Basically is a map, is a data structure, so it's a data structure that implements an associative array or dictionary, and basically is an hash table under the hood, use a dynamic array of linked list to efficiently store key value pair. So, if I go in the hash table here, you can see that basically what is doing, hash table is like a dictionary. For example, in Python, you see in Python, or a map, an hash map in Java. And say, for example, if I say Jack, if I connect the Jack, oh, just a second, it's not working, my pen. So just putting, this is the dictionary, or in JavaScript is the object, for example. So I have Jack, and Jack is connected, for example, with his age. I don't know, Jack has 57 years old. Is 57 years old. Poi we have Lisa. Lisa, suppose that is 45 years old. And then we have Homer, that is, I don't know, 50 years old. So this one is basically the how hash table, what is inside a hash table. And how it's work? Like I say, hash table basically is a dynamic array of linked list. And what does it mean? To understand the hash table, we have to investigate about what is the hash function and how this one is work for creating this dynamic array of linked list. So, like I say, hash table is very complicated, but in our course we see the key concept of how to use hash table and when it's better to using hash table. But basically it's a dictionary, a key value pairs, a system of storing the value. So here, like you see, there is a structure with 8 name. So and this is the for and for name that is connecting through an hash table. You can imagine an hash table like right now, like a black box. We can see it's very, very easy to explain, but for now, just a second, bear with me, and basically it means that is just a black box, And then we have the item 0, 1, 2, 3, 4. Because what I want to do, I want to store Jack, name Jack, inside one of these array. So how can I do that? How can I store Jack? Because Jack is a string. So remember in the memory, then we studied about the canvas. Here, of course, it's not an integer. It's not a decimal in a decimal mode. This one is binary. So it means 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. This one is in the 32 bits system. 0, 0, 0, and then here there is 11 in binary. I don't know how it's written. We can search very quickly. So I store in memory speaks not in string, but memory speaks in integer, in 0 and 1. So what I'm doing when I try to access, for example, there is a method in the dictionary on Python that you can call this dictionary, the dict, and you can call just Jack. Say for example, we can check with Jack, and then I can get the value that is, for example, the age that is 57. But this how can I do that? So basically, what does it mean that I'm searching for Jack? Because I cannot write Jack here. So that's what the hash function is doing. So basically, hash function converting Jack into a string. We can see, for example, some example. Convert the Jack as a string and store this string inside one of these array. Because basically an hash table is an array. Is an array of LinkedList. Here you can see an array that is in 0, 1, 0, 1, 2, 3, 4 position. Like we saw the previous one in the LinkedList. So imagine that the first four cells is just for 5. Sorry, the first 5 is just for our map, our hash table. This one is, imagine that is free to store our data, to store Jack, Lisa, etc, etc, etc. And this is the 5 position. How can I do that? So here I can introduce an example. This is just an example, but there is so many kinds, so many different hash functions, very famous, very powerful, very strong. Say for example, an hash function, what we can do is just putting Jack into this function. Jack is converted with ASCII convention. And then after ASCII, we can sum the value of the ASCII and do the percentage operator, the modulo operator, to get the remainder of my division. So let's say, for example, if I have my website, just for a second. So if I open my website here and I want to look, let's say, for example, string hashing ASCII, converter. So if I go into my code and I want to see, for example, Jack, just a second, I want to see Jack. So Jack, this is in binary, but let me for a moment converting in decimal. Okay, this is Jack. So I take this value. I cannot print, sorry. Let me just... so basically what I did is taking this value, sum this value, and after summing all this value, let's say for example I obtain 50, I do the percent, the modulo operator with 5, because 5 is the number of my cell. 0, 1, 2, 3, 4, that is 5 cells. I do the percent and I say, okay, the remainder of my division is 0. In this case is 0, because it means that 15 percentage 5, 15 divided 5, the total is 10 without reminder of my division. Say for example, if my sum of all my ASCII function is 51, the percent of course is 1, because the division is 10 without with 1, the division 51 divided 5 is 10 with the remainder of 1, of course. Here I do all this calculation for you. So basically, what does it mean? That Jack has this ASCII function, and this is with some encoding, and I think should be probably, if I go for example here, probably Jack was like this. Let me check. Yeah, so this is the Jack with the lowercase. Okay, but okay, let's skip for a moment. What does it mean? That the total number, so I convert the Jack, this string, into an integer, because computer PC speaks only the ASCII, speaks only in integer format. So I converted this Jack into a string. Then this string, I sum all the value. This is an example of hash function. Of course, there is so many different type of hash function that could be very powerful, very good to convert, to assign, basically, because we need to assign Jack into one of this array. This is our array. So, and here in this case, 409% modulo operator of 5 is 4. So that means that I take Jack and I put in here in the 4 position of my array. And then I do the same with Marta. For example, I convert into ASCII, and then I sum all the value and I obtain 1. So I take Marta and I'm putting 1 in the 1 position. And I do the same with Lisa, that so converting in ASCII, sum all these values, obtain 393, and 393%, the modulo operator of 393 is 3. So I take Elisa and put in here in the 3 position, and I do it again with Momer, with Maria, with Harry, with Eric, and with John. But what's happening with Harry? What's happening with Harry? Because Harry has the same modulo operator of Lisa. So how can I store in this array? So I have only 5 position. How can I store 8 value? Because it's 80 key value pairs. How can I store it? This is about what we call the collision. Collision is an extremely important concept behind the Hashmap. Sorry, just a second. Okay, this is a very important concept about the Hashmap, the concept of the collision. Collision means that my hash function, at one point, let's say for example we have 2 billion of data that we want to create. We want to create an Hashmap. At one point, I complete all my array. There is a different kind of solution to collision. For example, a solution could be involved, let's say for example that here I have only, I don't know, probably I have only 5. I have only 5 names. Let's say for example, if I clean, just for a second, I want to clean all those nodes. So let's say for example that I want to work only with, just a second, I have to erase it here as well. I want to work only with Jack, with Marta, with Lisa, Homer, I don't want Homer, I don't want Maria, and I want Harry, and I want Eric, and so that's it. 1, 2, 3, 4, 5. Okay? And what I can do is just say for example Jack go in position 4, Marta go in position 1 and is good, Jack is good, Lisa go here, and then let's say for example I have Harry. But Harry, what I can do is just, I have two options. This is a scenario of collision. When I arrived at the name Harry, I have a scenario of collision. What I can do is just, or I created a linked list inside this 3 position. I connected a linked list and then I connected Lisa with Harry. Or what I can do is just putting Harry in the position 2, for example, because the position 2 is empty. So I can create a reference in the position 2, fill the position 2, and then moving to Eric. Eric, there is another scenario of collision, but this time with Jack. What I can do, if I can search if there is some space in the memory and the 0 position, because imagine that we don't have Maria, just for a moment, the 0 position is empty, so I can put Eric in the 0 position. This is a solution to solve the collision problem. But usually it's not usually, actually it depends. It depends on, for example, if my function has a huge collision probability. Probably the best option is using the empty space in the array to fill the value. But otherwise, another things that I can do to save to collision scenario is creating a linked list. So basically what I'm doing is just connecting Lisa to Harry. So let's say a scenario when I want to search, for example, the age of Jack. Or the age of John, sorry, the age of John. John has 16 value, is 16 years old, say for example. So what I can do is, so I convert John in ASCII, I do the module of John, and I obtain 4. So I know exactly that is in the 4 position. And like we say, the array accessing at a given index in array is O of 1. So extremely fast in constant time operation. So when I have Jack, when I search for John, I go here. But then I have a linked list inside this array. So basically this array has a reference to a linked list, and the linked list as a reference to each item. So I have to search for John. And like we say, searching in John is an operation of O of n. So I got, it's not, sorry, O of n, but we can say O of m, because n, we can assume that is the size of the hash table. In this case, it is, for example, 8. In this case, it is 8. Let me just adding again Maria, Homer, etc., etc., etc. All of this number I can add all of these. All of these name. So n is the size of the array of the hash table, but m is the size of the sub-linked list. In this scenario, I have 3. So in this case, searching for Jack is very fast as well, because accessing to the 4 item is extremely fast, and then I have to search it in a linked list. And here the concept behind using so like we say here, this one is the array and this one is the linked list. That's why an array basically is an hash table basically is a dynamic array of linked list, because I can have in each position a linked list if there is a collision. Of course, there is extremely good hash function. This is very basic hash function that I show you, but could be very extremely powerful hash function that can help us to find the good item, the good value of the that help us to find to avoid the collision. So saying that, inserting the operation of inserting a key value pair of the operation of inserting a key value pair in an Hashmap. What is the average time to inserting a key value pair? Basically, the average time is O of 1 because it's extremely powerful. The hash function is extremely fast. So say for example I want to add, say for example that I have only this one, only the previous value, and I want to add John in extremely fast way, converting in ASCII, getting the sum, do the modulo operator, obtaining 4, and I had an item very fast. Sorry, John. But what's happening here, for example, in this worst scenario? If, for example, I have an array list, I have an hash table, that is an array list with all those items in the 4 position. And here, this is the worst scenario. And this worst scenario, I have O of n. But this is extremely infrequent. So on average, we can always, let me use for a moment the name always, because the hash function is extremely powerful today. So the hash function take O of 1 to go inside to inserting an item in a hash table. What about removing an item? The same fact. O of 1 in the best scenario, in the average, sorry, not the best, in the average scenario, and O of n in the worst scenario. Looking up a key here as well. So the operation to say, for example, I want to get the age of John. This is the key, and the value could be, I don't know, we say 16 years old. To get the age of John in the average scenario is very fast. Say for example for Maria, very fast, 0 position. So I'm converting Maria in through my ASCII function. I obtain 0, and sorry for my mouse. And once I obtain 0, I can go very quick inside the 1 position. And sorry for Maria, so I have in the 0 position and I access the value. For example, Maria has 45 years old. She's 45 years old, and is 40, and access very easy to 45. But here as well, in the worst scenario, for John, I have to access, so I convert John in ASCII function, some old value, getting the index. Once I get in the X, I have to cycle my linked list, and like we said, searching for a value inside a linked list take O of n, has a time complexity of O of n. So we can say looking up a key in a hash table is O of 1 on average, and we can assume that we can say every time that is O of 1, but just for a second, thinking about the theory could be in the worst scenario, say for example, if all these items are inside the 4 position, so I have a 4 with a linked list of 8 numbers. In this case, looking up a key could be O of n time. So like we say, this is an array list of, this is the hash map, the hash table is array of a linked list, and we have to stay careful about the collision scenario. Now we jump inside stacks and queue. So stacks and queue are basically implemented through the linked list because we need a dynamic structure. So very simple to understanding how stacks and queue work, because here you can see in the face, the stacks picture and the queue picture. So we're gonna see in very fast way stacks, because it's extremely easy if you look in the face the stacks. So stacks use the last in first out, also called LIFO LIFO way to store the data. Because basically what it's doing, imagine like a stack in the real life, and we have one that is the first item that is pushed inside the stacks, 2 that is the second item, 3, 4, and to get, it's very fast to get the last item, to get the last item inserted, because I have the get. It's very fast because I have directly the reference to the 4. If I want to, in this case we can say that, for example, the pop operation that is the removing of the last item is extremely fast in stacks, because if I want to remove the last item inserted is very fast, because pop operation run in O of 1, extremely fast. But what about, for example, deleting the number 1? Deleting number 1 take O of n, because now we have all the concept to understand what does it mean, what we have to do. This is a linked list basically, so I have to jump to 4, to 3, to 2, to 1, and then change the reference to 1, accessing to 1, and then change the reference. So O of n to access to this item, and then O of 1 to delete, because in the linked list, delete an item is extremely fast operation, but I have to access to this item, and this costs me O of n. What about, for example, get the number 1? Get the number 1 is the same, take O of n. What about get the number 4, that is the last item inserted? This is O of 1 operation. So in some scenario, it's very good to have the stacks if I want to access or pop the last item in my element. What about the queue? The queue is another logic that is about first in, first out. So like a queue, the first, like when we are in the post, in the queue in the post, the first people that arrived in the morning is the first one that is served by the operators. So here as well, if I want to access to the first item inserted, the operation is O of 1. Instead, in the stacks, if I want to access to the first time inserted was O of n, here is O of 1. But on the contrary, if I want to access to the last item inserted in the stacks, the time complexity was O of 1, in the queue will be O of n, because I have to loop through my linked list, moving from 1 to 2, and then from 2 to 3, and then from 3 to 4, and then I can get my value. And even here, if I want to push, if I want, for example, to removing the first item, or adding the first item, or update the first item, it could be extremely fast. The first item inserted, it's extremely fast. But if I want to, if I want to insert, if I want to insert an item in the first position at the head, it's extremely time consuming, is O of n. But if I want to push a value at the end of the queue, is extremely fast operation, because this one is only O of 1. And this is basically the concept about the queue. Once we understood how linked list works, we understood in a very easy way how the queue is working and stacks is working. So now we're gonna speak about the graphs. So like we said in the previous lessons, like we said before, here we are going investigating the non-linear structure, the graph for the first one, and then we will see the tree. So basically this is a very high concept. The graphs is a collection of nodes, like we see. This is the nodes, that also called vertices, and this is the edge. Some people call it branches, but basically this is the structure. So a graph is a collection of nodes or values called vertices that may be related, maybe not. And relations between vertices are called edges. A graph data structure consists of finite and possible mutable set of vertices. We can call the vertices, like we say, nodes or points, together with a set of unordered pairs of these vertices for an undirected graph, or a set of ordered pairs for a directed graph. So here we can see there is so many different type of graphs, but here we are gonna see only the basic, the most common, the most popular graphs. So for example, the cycle graph, a cycle graph, directed, disconnected, connected, undirected. So what is a graph? First of all, before starting to speak about the cyclic graph, we need to understand what is a graph cycle in the graphs theory. So basically, a graph cycle is a cycle, so is a non-empty trail in which only the first and the last vertices are equal. So basically here you can find a cycle. So I start from the 5, going to the 7, going to the 2, and the end I have again the 5, the same nodes. So this one basically is a cycle, like the concept that we see, so is a path closed, a trail closed. And here it's easy to understand that a cyclic graphs is a graphs that has at least one cycle. So let's, for example, this one, but even this one, if I say, for example, 2 connected to 7, connecting to 5, that all is connecting, and the 7 is connecting to 8, 8 is connecting to 9, 9 is connecting to 10, and to 11. This is this is a cyclic graph, because there is at least one cycle. A cycle is a graph. The cycle is a graph where there is no cycle, zero cycle. Directed, basically, like we introduce the concept of the arrow, because directed means that I can navigate the graph only in one direction. Say, for example, from 7 to 2, from 7 to 8 to 5. Sorry, I cannot go back, basically. So that's why we introduced the undirected graphs. Is a graph when I can go back from one item and I can go forward to the same item. And then another concept is behind the connected and disconnected. So connected basically means that all of the nodes inside the graphs are at least an edge. And disconnected means, so here, for example, this one is a connected graph. But let me jump for a moment. Let me remove it because it's not very clear to see. So if, for example, I do just 2, for example, connected to 3, connected to 5, connected to 4, to 4, and then to 5, and then 5 connecting to 8 and to 9. This one is a connected graph. And I say, for example, if I add a 7 here and a 8 here, this is a disconnected graph, because in the disconnected graph, I have not one of my nodes has not connection. And this is very powerful because this one is a way to represent hierarchically data structure. So this one could be very handy, for example, in the Wikipedia page. The Wikipedia page, basically, this is a cycle graph, because every page is a cycle, is a graph. Sorry, not always is a cycle, but Wikipedia page is a graph, because everything is connecting. Basically, we have to stay careful to some point. For example, speaking with the graphs, we have to stay careful of course, in the context of computer science, we will let me know in a comment if you want to see some examples, some implementation in Python of the graphs, how we can use the graphs during the implementation. But basically that's it. It's the graphs theory is extremely intuitive theories, very simple to understand, is so powerful in many different scenarios. But just to give you a point about the graphs, stay careful to avoid a loop in the graph. Say, for example, if you want to search, for example, a value, stay away from loops. So, for example, here it could be an infinite loop. Say, for example, I search for the number 8. 8 is never present. So I go through these connected and undirected, because remember it's a undirected graphs, and I can go through these loops and search for an infinite. I cannot find 8, for example, and I never get the response if I don't stop the nodes. So, for example, a system could be I mark this node like visited, this one like visited, this one like visited, and then I can go out the loop. Say, for example, but for example, inside the nodes you can store the list. There is very different scenario to work with the graphs in general, and a very specific concept behind the graph. We can say the child of a graph could be the tree, and the tree basically is a graph, but is acyclic, so there is no cycle inside a tree. Each node can have only one parent, and is a not disconnected graph. So every child has to have a parent. So basically this one is the tree, and so what we can say about the tree, that the first item is a root. The nodes are connected with the nodes, or leaves, or leaf nodes, also called, are connecting through the branches, and the most number of my item take the name of 8. So the deepest basically path that I can have in my tree is the 8 of the tree. In this case is 4. Let's say, for example, if I remove the 7, the 8 is just 3, because the maximum step that I can do to arrive at a hand going to the branches could be 3. But in this scenario I have 7, so the 8 is, like we said, 4. And basically, so this is a graph, but a special graph. And about the tree is very powerful if we, for example, do investigating about the balanced, just moving. If we search, if we start to talking about the balanced tree. So just be careful, there is so many different of tree. We cannot, in this scenario, we cannot investigating about how much tree they are. But basically, if you remember, we spoke in the first slides, we spoke about the concept of log of n. So some algorithm run in log of n, and this is the case, for example, that the binary tree, particularly the perfect binary tree, it means that is balanced binary tree. You can see all the definition that we need inside my page, and here, if you go down, you can see all the definition about what is a binary tree, what is a k-hairy tree, what does it mean full balance tree, etc., and so on and so forth, like for the graphs. But basically we need to stay careful, because the binary tree is extremely powerful tool, because it's run in log of n. binary tree is particular. Here we cannot see, but basically each time, for example, you are searching for a in particular, it's not the binary search tree, but it's not the binary tree, but it's the search binary tree that is so extremely powerful, because in the search binary tree, let me take a look, for example, in just a second. I want to share with you the search binary tree. You can see an image here, and this one is so powerful because because basically in the binary search tree, if I have to search for the number 7, it's extremely good, because in the right part I see only the number that are less than 8, and in the right part, in the right branches, I can see only the let me just for a moment copy, and then we can remove it. Let me go here, let me go in the last slide. So it's extremely powerful because like I said, in the just for a moment, let me remove it. It's extremely powerful because in our scenario, this binary tree, so in the right part of the tree, let me open here again. Okay, that's great. Sorry, just a second. Let me take the pen red. Okay, in the right leaf we get all the value, so we get all the value that is greater than 8, and in the right tree we get all the value that is less than 8. And this is so powerful because if I search, for example, for the number 7, I know that I have to delete all this branch extremely fast. So even if I have 1 million of leaves on the right part, I have to skip I don't mind what I have on the right side. I delete all the right side and I go to the tree. I know that the tree, in the right part, I have the things that are greater than 3, so I can delete all this branch in a very fast way, and so I have to work with so less. I have to work with half of the tree again. Here I have 6, and then I look for the right branch, and I have 7, and now finally I found the 7. And this is so extremely powerful because every time I cut in half my data set, my tree, and the search binary tree, this is called the search binary tree, is extremely powerful and extremely fast data structure. I will add as well this kind of data inside my slide. And basically that's it. This is the video about the data structure. This is a crash course, I know. This is a lot of definition about what is the perfect binary tree, the balanced binary tree. We can investigate on that because we can say on that because the binary is a tree whose nodes have up to only and no more of two nodes. So let's jump here again. So this is a binary. This is a perfect binary. If I have, for example, here another child, this is not binary. And then we jump again in the next definition. This is k-hair tree. So this is one. If I have k child nodes, the perfect binary tree, a binary tree whose interior nodes all have 2 child nodes and whose leaf nodes all are the same depth. So it's not impossible. For example, this is not, let me just remove it just for a second. So this is not a perfect binary tree because here I have a different depth, a different depth of my branch, And then let's say, for example, a balanced tree is a so extremely important concept, the concept of balancing, because see, for example, I can have a search binary tree here. This one could be a search binary tree. No, sorry, because I have to have the nodes. But imagine, for example, for just a second, this is not a search binary tree, of course, but let's imagine for a second that this one is a search binary tree. And let's say, for example, if I want to investigating about the number greater than 2, sorry, less than 2, and so I have to cut this half branch, and then I got this, basically this is an array list, and like you see, this is not useful, because in the search binary tree are good stuff that the very important concept that is balanced. So if I cut one of my entire branch, I cut half item, and this is very good. This is extremely good, because every time I cut in half my dataset, and even if I have 1 million of row, with 3 iteration, I can arrive in. So the first iteration, I delete the first, say for example, the right branch, and then so I get 500,000 item. Then I delete again, for example, the left branch, and I have 250,000 item, and then again delete, and then again delete. In 10 passage, in 10 steps, I go, I don't know, probably I have only 100 item. And this is so extremely fast, because if I have a huge, even with 1 million data, the search binary tree could be extremely fast. So stay careful about this concept. And basically this is the lesson about the use of the data structure. So like we say, you can see here, we investigating about the data structure, the linear and non-linear data structure. We have the static, the dynamic. We have the hash. We cannot see here the hash map, but basically the hash map is an array, a dynamic array of linked list. So stay careful on this concept, and let me know if you want, if you have any question, put a comment, and let me know if you have any question that can investigate and study and explain for you. And let's talk to you in the next video. Thank you for watching.